So here, I'm afraid I'll need a different picture of the view. So here's what I drew with a picture drawing capability here. It's a slight map if I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that, and oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, very interesting. All right. Mark it. Oh, I've already seen that. Produce, no, like that. Gee, that's too much. Anyway, so we have this feature of structuring our material hierarchically, being able to move around it very well. When we get a hierarchy, such as I can show you here now, I can do things if I want to just say, I'd like to interchange produce and canned materials. Bingo. And they're all numbered rightly if I care to look. Interchanging them very quickly. Cans are going to get interchanged with produce. Say, let's save that version. So this tool, in pursuing those goals, one of our principal tools is this computer aid system. Let's talk about it as a system. There's a link sequence to jump in there too, where we talk about NLS, meaning online system, a very general term. It's going to be NLS for many, many years, an online system that will evolve. Right now we consider it to be primarily an instrument and a vehicle for helping humans to operate within the domain of complex information structures. Well, what do we mean by operate? Well, compose, study, modify is the place we started now. We know there are many other analytic things you could do, but we want to get around, study, and modify. And then to further information about what does complex structure mean. We're talking about complex structure and emphasizing structure because we say, although the content represents your concepts, there's a structural relationship between that content entities that should represent the relationship between the concepts of human thought. All right, we never can do that very well with linear text. So inside the computer we can represent that quite well. In fact, we can represent information structures in a computer that would generally be far too complex for you to study directly. But NLS serves as a tool to roam over that, navigate through a complex structure, be able to find your way and be navigating, move about it rapidly, and be able to see what you want to see at any given point. That's how we think of NLS as a tool. All right, these are all very important concepts to us because these, together with the bootstrapping, have told us where to start. We start by building an instrument that we can sit at and work during our day to organize the kind of working information we need as a task force developing systems. We need to write our specifications, our plans, our programs, our users' guides, our documentation, dialogue and control meta-language that we're using. Okay, to talk about control devices, we'll use this overhead camera shot where you can see the devices that I'm using. I use 3, and they're not all standard. We have a pointing device called our mouse, a standard keyboard, and a special key set we have here. And we're going to go for a picture down in our laboratory in Menlo Park and pipe it up that'll show you from another point of view more about how that mouse works. Come in, Menlo Park. Okay, there's Don Andrews' hand in Menlo Park. And in a second we'll see the screen that he's working and the way the tracking spot moves in conjunction with movements of that mouse. I don't know why we call it a mouse. Sometimes I apologize. It started that way and we never did change it. All right, as it moves up or down or sideways, so does the tracking spot. And the principles for its operation are quite easy to see. If you'll turn it over, Don. Can you hear me, Don? Would you turn it over and we'll see, right. Its principle is that there are 2 wheels that roll on the surface. But since they're at right angles and kind of sharp edges, one will roll and the other slide in one direction. Each of these wheels controls through a potentiometer with a voltage output sampled by an 880V converter, the numbers taken in by the computer at sample times as to what the horizontal vertical components are to be of where it should put the tracking spot. And as the mouse moves over a surface, then each of those wheels either slides sideways without rolling or rolls an amount that very closely duplicates the particular component of horizontal or vertical in the net motion it makes. All right, if you take a mouse and move it through some closed trajectory back to exactly the same point, usually the tracking spot won't come back to exactly the same place it was on the screen. And for that sense, it wouldn't work well if you're trying to trace maps or other figures and diagrams. But the way we use it continuously and exclusively is to watch the screen and to follow it around, and we use this merely as a device to move that tracking spot, and your eye on the tracking spot, you really don't care whether it follows exactly this or not. In fact, we've had it at times where our tracking device, you had to move in an arc like that to make the tracking spot go on a horizontal line. And people adjusted to it and would go like that to go in a straight line and wouldn't even know that they were doing it. Other features of the mouse are that it stays put. I can lift it and replace it without having the spot change, so I can adjust where I want it for my comfort. And these control buttons on the top are used quite a bit, and I'll show you a little bit later how some of those are used. Now, the keyboard in the middle is essentially a standard typewriter keyboard, except for a few special keys out on the side. The computer knows it instantly when you hit one and makes an appropriate response. This device over here is unique to us, and we always have to justify and explain it. We'll do it in reverse order. We'll explain it first. It provides for you the one-hand equivalent of what you can do with a keyboard. There are 5 keys, and normally each finger sits on a key, and depressing any one key at a time produces a character. And any 2 keys at a time also. And in fact, any combination of depressing, of which there are 31 combinations, bring me back to remembering how I should have gone through this. To go down another level in hardware design, there are 2 features we want to talk about here to bring out to you the way in which we've gotten the kind of responsiveness and flexibility we need in this instrumentation environment. So way off in Bill English's file, Bill was responsible for the design of all of our hardware. There's an outline he made of the way the controllers work for the I/O controlling. Now, from this line to the right, things that we added to a conventional SDS 940 system. And this is the swapping drum. It's got 2 buses accessing to 4 16K banks. The CPU has 1 bus, and the peripheral equipment has another. And the good work of Project Genie at Berkeley, an ARPA project that evolved the 940 time-sharing hardware and software, produced a very neat priority system on this bus such that it can say, I'll defer my access to a given bank until the CPU doesn't want it. Or I'll defer it once or twice or 3 times, but then I really need it, so give me priority. And in that way, this bank can slip in many accesses to these while the CPU is hopping from bank to bank in its successive accesses. We've taken advantage of that to put all of our control out here, a large 96 million character Bryant disk for giving backup storage for ourselves, our 2 display systems, each of which drives 6 displays, and all of which are refreshed out of core, and the input controller, which samples the keyboards, the key sets, the mice of each station about 15 times a second, and our printer and the ARPA network coupling here all come in through that same priority basis. So they can all be working full tilt, and we find that we get very low interference in CPU cycles being interrupted or interfered with, something like a ratio of maybe 1 to 1.5% here that it can't get when it wants to, when this might be running 50, 60, 70% of the available memory cycles that it can handle. All right. The input controller stuffs it into core without ever interfering with the CPU's process, and then just interrupts the time-sharing system if there's something new and says, hey, take care of this user. And the display system reads out of core in from a tree structure-like set of links to cycle itself automatically and take all that material, output it to the display something like 15 times a second without any interference from CPU requirements. All right. So that system has allowed us to have one time-sharing computer, take care of a lot of stations. Let me talk to you about the display systems, the other aspect of the things that we've built on here that are slightly unusual. All right, for that I'd like to switch to Menlo Park and get a view from a camera there and actually looking at the hardware. So these are the units that develop the displays. The computer constructs it right on a small high-resolution CRT, which you're focusing in on right now. And in fact, that's the CRT whose camera on the right, looking at it, is generating the text view that's being piped down here on my console. So as those are faded in and out between the two, you can just sort of compare them. So that's very nice. There's my mouse moving around in Menlo Park, my tracking spot. So our displays work with those being watched by commercial cameras. Look at my black bug. Commercial TV cameras, 875 line scanning rates with a fairly high resolution. Look at that. From there on out to the display station, the standard video microwave system. If we back up the camera shot a little bit, we'll see that we have a whole rack full of equipment here, serving 12 of them, but you'll notice quite a lack of cameras mounted on. We seem to have stolen them all for this show. So we only have several consoles that work right now because the cameras are mounted to give you these different special views. All right, there are quite a few advantages. We use this particular display system hardware technique pretty much as an expediency for an experimental in a matter of minutes because they're all available instantly by anybody from one of these terminals. But there's another degree of collaboration which is very important and which we're just going to be setting up in the next few months the hardware to do computer aid. But here we're going to set it up with a little bit of people aid too. So I'm going to establish a collaborative mode between me and another terminal. Bill Paxton's at a terminal back at SRI, and the first thing I do to do that, of course, would be say, hey, I'm going to, to call this command, we have to go into the executive mode and set executivity to a special level. Oops. And then continue with NLS. So that free demonstration of some of the versatility. All right, special command. I'd like to link to Bill, and I don't know what his terminal is right now, so I have to ask for somebody to connect me to him audibly. So Bill, will you come in through this intercom?
Hello, Doug.
Hi. All right, I need to know what terminal you're on, Bill.
13.
Okay, I'd like to have him see my text. And so this special thing, if I label 13, will switch over. So in his display, he sees my text. So I'll execute it. And sure enough, it does. But what's that running around? Well, if he's looking at my text, he'd like to have something to say about it. So we put on a marker, a tracking spot that he controls. So he's sitting in Menlo Park looking at this text, and he can point to it. But we've carefully reserved for me the right to control and operate on this, so my bug is more powerful than yours. But we can have an argument. Yeah. That's what they call a bug fight. So, all right. So in case you haven't been listening, Bill, we've been going through lots of examples and setting up in collaboration here so that we can go on into information retrieval. And we've set up now audio coupling, and then we're both looking at the same display, and that'd be very handy to work. We can talk to each other and point, and maybe later I could hand you the chalk on this blackboard, like saying, here, you control it. But let's stay this mode now and add another feature that hardware-wise is available through the kind of display we have. I'd like to see you while I'm working on it. So before I can do that, I'd have to set up my display, in a certain way. Set it up so I see it over like that. That leaves a corner up there, and I say, now computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it, and I can see your face, and we can talk. So let's do some collaborating. You're silent. Oh.
What do you want me to say?
Yeah. There's nobody here but a large audience, Bill.
All right.
All right. So let's go talk about information retrieval. And there are a lot of things I've been showing them and jumping around and finding your way, relating back to the portrayal I gave about NLS as an instrument on complex data structures. It shows them how we can get around and find things. I showed them the content analyzers to help locate things locally. You had a file kind of classifying retrieval stuff. Why don't we switch to it? Yeah, good. Hey, I can't point.
Oh, okay. You on 13 or 12?
12.
You're on 12, okay.